Okay, let's dive into this. Imagine you're looking deep into the infant universe, right? And suddenly, you spot a perfectly formed, highly structured disk galaxy that absolutely 100% should not be there yet, like REBS 25. It's an impossible early disk galaxy that is literally rewriting the textbooks. Welcome to the impossible early universe. The James Webb Space Telescope is completely shattering our cosmic origin story, sending back data that has astrophysicists rethinking everything we thought we knew about the dawn of time.
Which brings us to a really massive fundamental question for this explainer. Is our cosmic origin story actually broken? For decades, we had a solid, established rulebook for how the universe evolved, but JWST is peering further back into deep space than ever before. And, well, it's finding things that simply have no right to exist yet according to those rules.
Astronomer Eduardo Bañados perfectly captured the shock of these discoveries. He said, and I love this, "It's like discovering a full-grown adult in a kindergarten class." Just pause and think about that for a second. We're finding these supermassive, highly mature structures at a time when the universe was barely out of its infancy.
To understand why everyone is so shocked, we really have to look at our baseline expectation, which is the standard model of cosmology. This model basically tells us that massive galaxies formed very, very gradually. Picture tiny gas clouds and baby galaxies slowly bumping into each other, clumping together over billions of years. You know, slow and steady wins the cosmic race. At least, that was the assumption.
Section 1. Meet the universe breakers. The contrast between what we expected and what JWST is actually seeing is just stark. We expected this gradual formation, where galaxies slowly converted gas to stars at a low efficiency, maybe 20% or less. Instead, JWST is revealing a reality of rapid, almost speed-running star formation. Take the mind-blowing REBLS-25, for example. It's a massive, perfectly rotating disk galaxy found when the universe was just a toddler. These early galaxies aren't clunky. They're highly efficient stellar factories, just churning out stars right out of the gate at nearly double the expected rate.
Tracing the cosmic timeline, the crowding happens incredibly fast. So we start at the Big Bang. Then, just 500 to 700 million years later, these universe breakers, like RBLS 25, suddenly pop up, way too massive for their age. By 700 million years, we spot the little red dots, which are hiding these giant black holes. And by 800 million years, we're already seeing JWST's quintet, this complex multi-galaxy merger. The infant universe was just impossibly active. Now, what's really interesting is when we break down the data from these deep field imaging campaigns, the anomalies just pile up. We've got the red monsters, which boast stellar masses comparable to our modern Milky Way in less than a billion years. Then there are the universe breakers holding up to 100 times the expected mass for their era, meaning we probably need to alter our early dark matter models entirely. And JWST's quintet features 5 interacting galaxies merging billions of years earlier than anyone predicted. Let's zoom in on JWST's quintet for a second, because this number is staggering. 250. That is the amount of solar mass being turned into stars every single year in this one compact cluster. It's roughly 250 times the mass of our Sun being churned out annually. It is an astronomical rate of production that totally, completely breaks our standard models.
Section 2. The chicken or the egg. So this brings us to the ultimate cosmic detective story. Which came first, the galaxy or the black hole? We used to think a massive galaxy had to assemble first, right? To slowly feed a central supermassive black hole over billions of years. But JWST is throwing a wrench in that, asking us, how on earth did these central giants get so big, so fast, in the infant universe? In our local modern universe, a host galaxy is usually about 1,000 times more massive than its central black hole. The galaxy totally dwarfs it. But in the early universe, in mysterious little red dots like Abell 2744 QS01, we are seeing a 1-to-1 ratio. The black hole is just as massive as all its stars combined. This strongly implies that black holes might have actually formed before the stars in their host galaxies, which is wild. And speaking of massive, try wrapping your head around this number, 6 billion solar mass. That is the solar mass of a dormant black hole known as MRG-M0138. We're observing it at what astronomers call a redshift of 2, which simply means we are seeing it as it existed when the universe was only a quarter of its current age. 6 billion suns worth of mass just sitting there in the early cosmos. Now you might be wondering, how do we weigh something invisible that is 10 billion light years away? Well, the answer is a Nobel Prize-winning trick called gravitational lensing. Basically, a massive galaxy cluster sits in the foreground and acts like a giant cosmic magnifying glass. This allows scientists to measure the speed of stars whipping around the black hole in the background, boosted by its immense gravity, letting us calculate its exact weight.
So why does all this black hole stuff matter to our cosmic origin story? Because it means early supermassive black holes likely didn't need a massive galaxy to feed them. They might have formed directly from the collapse of dense, turbulent gas. And that intimate coevolution between a black hole's mass and its galaxy, known as the M-sigma relation, was already firmly locked in 10 billion years ago. They essentially grew up together from the very start.
Section 3. The Hubble Tension.
Let's define the ultimate prize in astrophysics for a second. The Hubble constant, or H0. This is the exact rate at which the universe is expanding. It's a fundamental number that reveals the speed of growth, the precise age, and the overall history of our universe. Basically, get this number right and you unlock the cosmos.
But we have a severe disagreement in the scientific community right now, known as the Hubble tension. Predictions based on the early universe, looking at the cosmic microwave background, give us one specific expansion rate. But measurements taken from our late, modern universe using exploding stars give us a noticeably faster rate. The two ends of the universe simply aren't matching up.
Enter JWST again. Astronomer Wendy Friedman and her team used the telescope's unprecedented infrared vision to cross-check this tension. To be absolutely sure, they didn't just use one type of star. They used 3 independent measurement methods simultaneously within the same nearby galaxies: Cepheid variables, tip of the red giant branch stars, and carbon stars. They wanted to be incredibly thorough.
And the number they arrived at? 70. Specifically, 70 kilometers per second per megaparsec. Why does this matter? Because this new measurement actually overlaps with the early universe models. It suggests that maybe, just maybe, the expansion rates do align after all, and the standard model is holding up.
However, the debate is far from over. While Friedman's JWST data suggests the tension might be resolved, other expert teams maintain that the discrepancy is absolutely real. If it is real, it strongly points to entirely new physics, like a mysterious early dark energy phase that accelerated the universe right after the Big Bang. The scientific community remains split right down the middle on this.
Which leaves us with a provocative final thought. Are we missing something fundamental in our physics, or is standard cosmology safe for now? From impossible early disk galaxies like REBLS 25 to massive primordial black holes, the James Webb Space Telescope is pulling back the curtain on a deeply mysterious universe. And every new observation promises to either validate our cosmic origin story or force us to write an entirely new one.